voice on. Very good. So we are starting kind of, this is sort of a preview first session starting in August. So we'll start kind of full force in September. We decided to start kind of this season with people who tend not to take vacations in August because they're based in the Southern Hemisphere, right? And that's New Zealand and Australia, right? And therefore we asked to speak today two well-known members of our community, Arkadii Slinko and Aziz. So this also explains the timing of the talk, right? So it's pretty late on Arkadii's site, I think as late as 9 p.m., right?
Yes.
And for Harris, right? Yeah, so we appreciate kind of the speakers making the effort to give this talk at an evening time. Okay, so kind of in terms of running the seminar, okay, so the talks are 20 minutes followed by 10 minutes questions. So during the talk, I ask you not to ask questions by speaking, by using the microphone. So I would ask you to keep your microphone muted for the 20 minutes of the talk, unless you're asked to turn it on by the speaker, by myself. So you are still welcome to ask questions. You can do so in the chat. So if these are questions to be answered by the speaker at the end of the talk, this is what's going to happen. Or maybe someone will be able to answer your questions, someone other than the speaker will be able to answer them in the chat. We sometimes have really interesting conversations in the chat, right? If this is a clarification question that would be important to answer during the talk, then I will monitor the chat and I will interrupt the speaker and ask him to answer your question. But yeah, please no voice questions during the talk, right? And then we'll have 10 minutes of questions after the talk, right? And this will be a mixture of voice and chat. So you can also raise your hand if you want to ask a question. So raise your hand button is available from the menu below. So we used to have a practice session where one would practice raising the hand. Ulla, do we still want to do that? Or are we mostly using the chat? Okay, so I already see something in the chat. What's happening there? Question. Yeah. So Ulla is demonstrating how to ask a question. Okay, so raising one's hand. Right, so there's this little hand icon. Okay, so Ulla, can you do this part, because somehow I don't see the hand icon kind of.
Yes, yes. If you're a co-host like you are, you cannot see the hand icon. But everybody else, if you go to the participants panel, you will see a little blue hand, and several people have found it and they're raising their hand right now.
Right. Yeah. Lots of hands. Yeah, it seems like most of you got the hang of it. Okay, so we are. Okay, good. So I think we are ready to start now. So 10:05. Okay, so Arkadii, would you like to start sharing your screen?
Okay. Is it visible?
Not yet.
Strange. Is it visible now?
Visible now, but it's not full screen yet.
Yeah, full screen is easy.
Okay, great. Now it's full screen. Okay, so our first talk today is by Arkadii Slinko. Right? Recently, Arkadii has been doing very exciting work about secret sharing, and in particular, the relationship between secret sharing and simple games, which are a core interest for our community. So today he'll give a talk about this line of work. This is joint work with Eva Desmet, a cryptographer, and Song Baumo. Welcome, Arkadii.
Thank you. Thank you very much for inviting me to talk here. So this talk is with a rather famous cryptographer from Dallas, Eva Desmet, and my PhD student, Song Bao. Okay, so this is about manipulation in some cryptographic context. So people in this group are very used to sharing a cake or dividing a cake. So lots of papers are written about this, but here we will do something different. We will fairly divide the power. So what is secret sharing? Secret sharing is a cryptographic implementation of a power sharing agreement in the society with respect to certain activity, be it accessing a Bitcoin wallet, launching a nuclear warhead, or signing a message on behalf of a large organization, for example, Adobe. Now, the power structure is given by the set of authorized coalitions who are authorized to launch the activity. And in the center of the implementation is the secret, which is a string of zeros and ones, which has no meaning whatsoever, apart from accessing this secret. You can further launch the activity under investigation. Okay, so in this paper, we consider the digital forensic aspects of secret sharing. Sometimes something wrong happens and investigation is needed to establish, for example, who made this suspicion transaction with Bitcoins, who signed this offensive letter on behalf of our organization, which led to a loss of a huge sum of money and litigations or whatsoever, who opened the vault in the bank. We investigate the problem of framing, which occurs when a coalition is able to calculate the share of a participant who does not belong to it. In the extreme case, one authorized coalition can calculate the secret, but it also can calculate shares of another authorized coalition and use those shares to access the secret, do something, and blame another authorized coalition for their actions. So access structure gives us is actually a realization of this power sharing agreement. So participants might have different status. Some may be more important than others. And access structure is a tool to reflect this. Access structure is nothing else as a simple game. So we have a set of participants. And there is also participant 0, which is the dealer who manages the scheme. So formally, an access structure is a pair of set of participants, usually denoted by gamma, the set of participants P, and the set of subsets of the power set 2 to the power of P, different from it's not, which is not empty, otherwise it's meaningless, which satisfies monotonicity condition that if X belongs to W and Y is larger than X, then Y also belongs to W. So this is nothing else as a simple game. Coalitions from W are called authorized, and coalitions which are not in W are called not authorized or unauthorized. Now, the classical example of access structure, Shamir in 1979 suggested 2 types of access structures. Firstly, why did he suggest that? Because he said that some information are so valuable that you cannot store it on a single server. You have to distribute it, for example, between 3 servers in such a way that intruder into each of them will find no information about this data, but from any 2 servers you can recover your data. So if one single server is hacked or stopped working, you will still be able to recover the data. Especially decryption exponents of RSA crypto system, for example, is one such valuable piece of information that needs protection. So K out of N structure coalition is authorized if it contains at least K people. Very standard. Another access structure suggested by Shamir is weighted threshold structure, known also as weighted simple game. So there is a weight function which assigns non-negative real number weight to each participant, and also a number Q non-negative quota is set, and the coalition is authorized if the total weight of this coalition, sum of weights belonging to members of this coalition, is at least Q. So such simple game is usually denoted in this way. You list Q and then weights of participant players. And this is so-called weighted representation of gamma. But in secret sharing, weighted threshold structures are not very popular. I will tell you later why. Let's look at other access structures. So assigning weights would be one way to introduce seniority, but weights usually badly reflect seniority of participants. So there are other ways of doing that. In particular, here the access structure suggested by Siemens in 1990. So we have 2 classes of participants. We have group P1 and group P2, and they are interchangeable within each group, so one can be easily replaced with another without any changes. And for every coalition X, we have first component X1, which means those X which belongs to P1, and we also have X2 part, which is those element of X which belongs to P2. And hierarchical disjunctive structure has 2 parameters. They are actually multi-dimensional parameters. Here, for simplicity, I take 2 as a dimension. So n is 2-dimensional vector, k is 2-dimensional vector, n is n1, n2, and k is k1, k2, and k1 is smaller than k2. Now, n1 is the number of participants in P1, and 2 is the number of participants in P2, and k1 and k2 are 2 thresholds. So the authorized coalition X will be, the coalition X will be authorized if it has at least K1 participants from the first. It will be later shown to be senior group, or alternatively, K2 participants in total. There must be some little restrictions on these parameters, not to make this trivial. Okay, so, but later, some later, Tassa, that's cryptographer from Israel, introduced hierarchical conjunctive structures, which are different only that you have conjunction sign here, not disjunction. So coalition is winning if it contains at least K1 members from the first group and at least K2 members in total. So to give just one example, the UN Security Council is such conjunctive access structure. It has 15 members, 5 permanent, 10 non-permanent members. The passage of resolution requires approval of at least 9 countries, subject to a veto by any one of the permanent members. So it's official, which means that it's conjunctive with parameters N1,5 and 2,10, K1,5, all permanent members must vote, and K2,9, because 9 countries must vote in total. So it's conjunctive scheme. It can be also shown that it is weighted structure with threshold 39, weights of permanent members 7, and weights of non-permanent members 1. Now, in game theory, there is a desirability relation, which introduced by Isbell in the 50s, which means that which participant is more desirable as coalition partners than another. So intuitively, we feel that in the previous examples, participants of level 1 are more important than those of level 2. We can formalize that, introducing a relation, which depends, of course, on the access structure gamma. And P is at least as senior relative to gamma to Q, if whenever X with Q is authorized, then it is also authorized with P. For every coalition P, for every coalition X, which doesn't include P and Q. So roughly speaking, P is at least as powerful as Q in relation to gamma. So this is, as I mentioned, that's Isbell desirability relation. So let's look at Shamir's scheme first. It's called threshold access structure of K of N access structure. The secret sharing scheme is access structure, which is a simple game, plus something on the top of it, which actually implements this power sharing agreement. So let's see what is on the top of this threshold access structure in Shamir scheme. So we take a large finite field, so large that it's infeasible to guess any particular member of it chosen as a secret. Then if we have n participants, we also choose n distinct elements of F, which are public knowledge. And now, if we have secret to share, which is element of this field, what the dealer does, it could be done, of course, by a computer. It creates a polynomial, and a constant term is a secret, and then k minus 1 absolutely random elements, and then he forms a polynomial. Now, what are the shares user I gets the share Si, which is P of AI, the value of at AI of this polynomial P of X. So the dealer gets, of course, P of naught, which is a secret. Now, clearly, this scheme realizes K out of N access structures, because if K participants get together, then they will have known K values of polynomial of degree K minus 1. They will reconstruct all the polynomials, including the secret T naught. But it's possible to show that if K minus 1 participants get together, they will have no clue about T naught whatsoever. Well, this is a simple pictorial illustration of 3 out of 4 scheme. So C is a secret. It becomes a constant term. So we need 3 out of 4, so we need a quadratic polynomial. A, B are random, and then these guys get f of 1, f of 2, f of 3, f of 4. If 3 of them get together, they will know 3 values of a quadratic, so they easily reconstruct the polynomial, and they will know C. Right, but there is a problem with this famous scheme, because these K people will reconstruct the polynomial, and they will then be able to calculate all the shares given to other participants. And since these are publicly known values. So in particular, this makes forensic investigation impossible, because now they can submit for recovery of the secret any pretend to be any other coalition. Now, linear secret sharing allows us to construct secret sharing on the top of not K out of N scheme, not K out of N access structure, but for some access structures where some participants are more important than others. So we start with n plus 1 row vectors of K-dimensional vector space. We put them as rows and generate a matrix H, which is n plus 1 times K matrix. And then access structure defined by this matrix H will be as follows. So a set of indices I1, I2, Ik will form an authorized coalition if H naught, the dealer's row, can be spanned by rows belonging to these participants.
Wrap up in a couple of minutes.
Sorry?
Do you think you'd be able to wrap up in a couple of minutes, because we're getting to the end of the slot?
Ending to what?
We are getting to the end of the slot. The talk slot proper was 20 minutes, and I think we're getting to the end of that.
Okay. How many minutes do I have? Do I have 5 minutes?
5 will be okay, but we won't have much left for questions then.
Okay. Okay. So the secret linear secret sharing works similar. We generate K plus 1 random value, then multiply H by get shares of participants, and then if H naught is spanned by H1, H2, K, then secret will be recovered in a similar way. So this is example. You see that these 2 rows span H naught, so 1 and 2 will be authorized, And then any three will be also authorized as well. So this is disjunctive hierarchical with K, 2 thresholds, 2 and 3. Now, ideal secret sharing scheme is ideal if it is, firstly, it's called secure if unauthorized coalition can get no information about the secret. Now, there is a famous theorem which says that a secret, this scheme cannot be secure unless the length of any share in bits is at least the length of the secret. And if it's exactly the length of the secret, then the scheme is called ideal. Shamir scheme is ideal, linear schemes are ideal. Weighted threshold structures are seldom linear and seldom ideal. So there is a famous characterization of ideal schemes. Each scheme is attached to a certain matroid, and the access structure of ideal scheme is a port of this matroid. So we are not using this theorem, but we heavily using the machinery of this theorem. Now, the main theorem of this talk is if you have an access structure of an ideal secret sharing scheme and an authorized coalition, and a participant in this coalition, which is pivotal, so which is without it, coalition stopped being authorized, then X can frame any other participant A who is at least as senior as B. Now, it's tempting to suggest that if members of coalitions are more senior than any other participant, then they cannot frame these participants, but it's not exactly true. There is an example. This is true if a coalition is shift minimal authorized coalition, which means that if you replace any coalition, any member of a coalition with a weaker one, it becomes losing. And then another main theorem says that if X is minimal authorized coalition in ideal hierarchical scheme, then it's shift minimal if and only if X cannot frame anybody who is more junior than any member of this coalition. Now, what is important? Let me, so this framing thing is a price that we have to pay for using an ideal secret sharing schemes. If you want to have optimal scheme, information-wise optimal scheme, then there is another price that you have to pay. So this this framing is a side effect of using ideal secret sharing schemes. And it's interesting that junior people can frame senior people, but not the other way around. Well, there are some cryptographic techniques that can prevent framing. You can add authentication tags to shares. You can encrypt shares, or you can encrypt the secret, but all of them can be bad in some circumstances and some good in some other circumstances. Well, that is effectively the end of the story.
Thanks, everybody. So let's all unmute our microphones for a round of applause.
Well, I thought sharing, huh?
Okay, yeah, and there's some virtual see in Zoom. Okay, so I see so far, I see one question in the chat. Arkadii, can you see it as well? Or shall I read it?
I see four. First question, how I ask question.
Right, no, so there's a real question at the very end of the chat, if you scroll down to the end.
A scheme where the arguments are not public but secret between the dealer and the individual users. the tradition of the secret sharing that the access structure must be a public knowledge, so that everybody should, everybody knows who is authorized, who is not authorized, and why these are made known, because then it becomes ideal. Because the secret is an element of the field, and the share is an element of the field. So if you want to give more information to participants, then it stops being ideal.
But the point is that it then cannot be framed.
Sorry?
You cannot frame another user then, because though you know the polynomial, you still don't know his part of the secret, so you cannot simulate that.
Yeah, well, there's one way of trying to avoid framing is making a scheme not ideal. And there are many ways how to do that. But if it's ideal, then framing exists. And you can make it non-ideal in several different ways, and then you can try to minimize or prevent framing.
Okay, do we have further questions? You can ask them in the chat, you can raise your hand. Oh, I have a question of my own, so that's a clarification question. So, Arkadii, so initially when you talked about framing, you talked about one coalition framing another coalition. But in the technical result, it was, framing a specific, more senior member. So what does it mean to frame an individual?
Calculate his or her share.
Oh, so just that.
And you can do the following. You can calculate somebody's shares, you can publish it, and by doing that, you can actually change the access structure. There are lots of manipulations that you can do when you calculate somebody's share.
Okay. Further questions from anyone? No, then, okay, so our timing is actually perfect. We are 30 minutes since the moment Arkadii started speaking. Okay, so let's thank Arkadii again.
Thank you.
And yeah, so now we have what some of us consider the most exciting part of the seminar, the virtual coffee break. So Ulla, will you explain how you're going to run it?
Yes, so we're going to randomly allocate you to some breakout rooms. So then something will pop up on your screen and you hopefully will accept the invitation. Then it takes a few seconds and you get taken to this other room and you can talk to a small subset of the people here. And we see you back after 10 minutes.
Right, and then it will be Harry's turn. See you then.